So this is the third in the series. We've run digital industry, mobility, and this is healthcare. We also are running our Meeting Mojo, which is the networking app that allows you to connect with other delegates and have conversations now and going forward. So if you haven't already had a look at that, that's something to consider. And our agenda for today. There is one slight change. Unfortunately, our presenter on the detection for falls in the elderly has had to cancel at the last minute due to illness. We will endeavour to get their slides sent out to people post-event anyway. As you can see, quite a packed agenda there, as well as the regular presentations we have from our invited speakers. We've also decided to come up with some short presentation slots today. If you're doing one of those short presentation slots, as I say, my colleague Aileen, who's running the program for me in the background, will be enabling your microphone. When we get to that section, I'll introduce your project. If you could then take yourself off of your microphone, that'd be great. You have 4 minutes in which to pitch. I will pop up and give you a quick wave when you're getting towards the end of your time. I think that's it, really. We're hoping we will still finish on time because I have a feeling that some of the presentations could be really interesting and get a really good panel. If you have questions at any point, please put them into the Q&A box, and I'm going to be saving those up for the panel Q&A at the end of the presentations. So there'll be no questions after each presentation. Right, so that brings us, that's how we're going to run today. I'm now going to stop sharing my screen. And I'm going to, sorry, I'm going to introduce you to Elizabeth, who's going to be giving our first quick welcome in a sec. I'm going to start off with a quick hello on behalf of the KTN. So we've been hosting this series, working with EPoSS now for several months. KTN is Knowledge Transfer Network in the UK. We are here to help the innovation landscape. The simple version is PPP, people, products, and pounds. We help the innovation space and innovative companies connect to other companies, to other organizations, and we help people source and find funding. We're based in the UK, but we also work with people like DIT, with companies looking to bring to the UK and helping people export expertise and technology outside of the UK as well. So our job here to bring these communities together on electronics and embedded systems is what Nigel's been driving with today. So I'm just helping out to get this last event of the year off on a really interesting topic of healthcare with a really diverse set of speakers. So I'm going to turn my mic off now and pass this over to Elizabeth to give us a quick talk.
Good morning, everybody. So it's also my pleasure again to welcome you to this third webinar. Today I'm going to show you give you a quick overview of the ECSS RIA. So can you see my slides?
Yes, all good.
Yep, everything's fine.
Thank you. So the ECSS RIA, that's the Strategic Research Innovation Agenda for Electronic Components and Systems for Europe. And I had the pleasure for EPoSS, on behalf of EPoSS, to share this, the generation of this major update that has been published very recently. And I just want to give you a very quick sneak view on it, and then later on encourage you to have a look at it and give us your feedback to the document. So a very brief look on the history of this document. So first of all, it is a common document of the three industry associations, ENEAS, Artemis, and EPoSS. So it's covering the whole value chain for electronic components and systems, from the microelectronics up to cyber-physical systems and systems of systems. In 2014, we started with 3 different SRAs covering only part of these, and in 2017 the first common version was published, and now I think for the first time we really have a concise document where you cannot really recognize which part of it comes from which kind of community, because it's really a merge, I would say, of technologies that we now have here, and that we implemented in a new structure, as I will show you in a few minutes. So it is a funding agnostic document that we created here, and it's looking ahead 10 to 15 years, and it serves as a basis for funding instruments. So the former versions were giving the input to the Excel joint undertaking, and of course the plan is that this version that is currently being published will lay the ground for a new joint undertaking called Key Digital Technologies, and should last until 2030. So saying this, it is even going beyond, because I said it is funding agnostic. So it is not only made for the European Commission instruments, but it's also the basis for Eureka clusters like Penta and Euripides. And we are currently preparing the white paper for a new electronic and components cluster following these two clusters. And so it will also be the basis for calls in this environment. So especially with people from the UK, not after Brexit being really involved in the European calls, Eureka would really be a good opportunity as well for common European projects, because it's the UK supporting this. So having now a look at it, so first of all, it has been published on November 17th. It has been created by a huge team, and it's open for having a look at it. So you can find it and download it from the EPoSS website, but also from the websites of the other industry associations. And you can still give us your feedback, but you have to be quick, because the deadline for giving feedback is next week. So so what is new in this document? Well, we came up with a completely new structure to really show how the different layers in the electronic components and systems are interacting, and how to cover the whole in one document. We have analyzed a lot of major challenges that we identified bottom up in the different chapters, and we came up with 4 main objectives for Europe and for our ECS community. For the first time, we really developed common global timelines, short term, which means for 5 years, midterm 10 years, and long term 15 years. So we broadened the scope of the whole thing by really integrating topics from integrated photonics as well as from flexible electronics. So really bridging out also to new technologies that will be of utmost importance for future electronic components and systems. And we created a common glossary, which is really nice to get a look on for definition of the different topics we are covering, because we identified, working in this really huge team coming from different communities, that talking about a component does not mean that people have the same part of a system in mind. So we took quite some time to really find a common speech, and we last but not least created then an executive summary for decision makers. So the new structure, very briefly, it starts with foundational layers. So we really cover in this chapter 1 all the process technologies, starting really from the bottom, from the materials, from the equipment and the manufacturing, and then we go along the layer stack to components, modules, and system integration, a topic where especially the EPoSS community is, of course, very active in. And then we have a subchapter on embedded software and beyond. And last but not least, and I think this is really going one layer above from what we did up to now in our SRIA, we have a subchapter on systems of systems. So But I think what is the real new thing is that we identified that there are really cross-sectional technologies that go through all the layer stack that are of really high importance for future developments. And the first subchapter here is artificial intelligence, edge computing, and advanced control, because this is what we are talking about today. So artificial intelligence, edge computing are really important topics to be covered along this whole stack. And the same holds for connectivity, of course, 5G, 6G developments. Then as a basis for all our activities, a chapter on architecture and design, methods and tools. And last but not least, quality, reliability, safety, and cybersecurity, which also have to be developed along the whole foundational layer stack. And last but not least, we have, of course, the key application areas, the drivers for our developments, and there we cover the chapter of mobility, energy, industry, and of course the topic of today, health and well-being, as well as agri-food and natural resources. This is a brand new chapter, and we have a chapter on digital society, having more a look on what the personal needs of people are. And so this gives you a quick overview of what is in the document, yeah, and so should help you to find and identify the right chapter to read. And then, as I said, we have picked up 4 main objectives when we analyzed the major objectives of the ECSSRA. And so one of it is boost the industrial competitiveness. The second one is ensure European digital autonomy. And third one is, of course, sustainable ECS for the Green Deal. And the third, but also very important one, is the European digital age. So, and everything that we can contribute to that. So we aligned everything along these main objectives, and we came up with these very common timeline here. So this is already a condensed one. So looking into the details of that would take more time than I have today. So this is, as I said, is just a sneak preview on what you can find there. So please have a look at it and give us your feedback. And yeah, so thank you very much for your attention. And of course, this is not just, it's one of the electronic components and systems as RIA is, of course, embedded in a whole global landscape, but we are core for a lot of these other activities going on. And so just let me finish with that, and thank you for the attention. And as I said, it's open for feedback, but you have to be quick. Thank you very much.
No worries. Thanks very much for that overview. And as you say, be quick if you want to pop an idea in there. So just to say that, Elizabeth, we have a question in the Q&A box if you wanted to pop over there and have a look at that. I'm now going to hand over to our first presenter of the day, which is Nicholas Goose. Over to you.
Yes, thank you, Simon. Here, that should be now here. So, yeah, thank you for giving me the opportunity to introduce actually the topic of AI, the age, and healthcare. I will provide this overview on behalf of EPoSS, the European Technology Platform on Smart System Integration, and particularly on behalf of the Working Group on Healthy Living. That's the group of members who within this European technology platform discuss strategic and technological developments linked to the increasing use of smart systems in healthcare and in well-being. And of course, in order to provide technological solutions to this application domain, we have to take into account the different specificities in this field, which is quite complex in terms of industrial value chains, in terms of regulatory frameworks, market requirements, but also the impact it has on the society in general, and through that, the political significance of the healthcare sector. And that's basically the way we are working in this working group are on different approaches. First, a kind of multidisciplinary approach. We have a real mix between universities, research centers, but also quite a lot of SMEs and also larger companies. So we are able to build up a kind of ecosystem here to discuss these issues in health tech. We have also a cross-fertilization approach, meaning that this working group is not a silo within EPoSS, but we are exchanging with other vertical, so applicative working group, but also horizontal, so the technology-based working groups. We also have participative approach based on open consultation of members. So we discuss the topics all together. We have consultation also to contribute to different strategic papers. We just saw the example of the ECS SRA from Elizabeth. And beyond the EPoSS community, we also quite a lot of links with the outside from the different partnerships that will be also set up in the framework of Horizon Europe, but not only, also with some platform dedicated to health technologies. For instance, Health Tech for EU, we signed a memorandum of understanding for them in order to build up forces and to join forces to provide the best innovation in healthcare. And that's the principle we are following when we are discussing the future of smart systems. And that's something that Elizabeth already mentioned. There's a shift in electronics, and the fact that we are broadening the scope to photonics and to diverse technologies, we have to think of a new layer of electronics, and that's the results of some EU project we are conducting together with EPoSS. That's a 5E project here, where we develop a concept for functional electronics, because we see that we need a higher degree of integration, and we need to speak about functionalities independently from the underlying technologies. And the topic of AI at the edge, for instance, is really crucial to realize a specific functionalities, which is more the computing, processing, and data treatment functionality. But each functionalities that are realized by the electronics are should be combined in order to provide solutions. And that's why we analyzed in the 5E project that processing and AI at the edge is always in combination, mostly of sensing functionalities, but also a lot of interactions with energy, powering, communicating, and of course actuating. So that's a major trend for electronics. Another trends, this time more in healthcare, and that's also the results of another European project we are linked to, that's the Nobel project. We see that healthcare and the way healthcare is provided is changing, and I guess, I hope that technology and innovation in electronics, in digital technologies, is helping this shift in healthcare from a centralized healthcare with some silos, hospital, doctors, and so on, to a more decentralized model where health technologies help to prevent disease, help also to have or to attenuate or to delay the acute phase with the introduction of a pre-acute phase where diagnostic and monitoring play a crucial role. Health tech also reduce the intensity of the acute phase with personalized medicine, with a monitoring during and after treatments, for instance, but also with a lot of rehabilitation so that people can go back to their normal life or quite normal life as soon as possible, and with a better quality of life. And even if some chronic disease require monitoring over the long time, there are some solutions also to improve home care in this respect. So that's a second major shift in related to health tech or innovation in healthcare. And that's why it's important to take that into consideration when considering HAI and healthcare, because it's offering a lot of perspectives along this continuum of healthcare, from prevention to diagnostic to home care, but also a lot of requirements along this this continuum. So we need some useful information that also should be exchanged between the different actors, between the different places. We need safe operation. We need increased performances. We need also an improved autonomy of systems. And that's something that the European Commission also stress in the future framework program. We need also human-centric perspective beside considering also sustainability issues. And this set of requirements are also places where HAI can act and can provide some solutions. So for instance, seamless operation. We need some technologies to provide that. And I would say the closer to the body, the safer operation should be. And the image here is, if you're driving a self-driving car and going into a tunnel, you don't want the intelligence to be in the clouds. You want the intelligence to be in the car, in the tunnel, in order to come out from the tunnel safe. And that's quite the same here with healthcare devices. You want that the intelligence provides some safety in operations and provide no disruption in any conditions. But HAI also provides some an increased self-sufficiency in terms of automation, and provide a higher level of automation device, but also self-sufficiency in terms of energy management, better matching power and consumption. So providing maybe some lifelong and battery-free operations, but also have the potential to reduce the maintenance burden, and potentially also to have maintenance-free health tech devices. And the best examples here are implantables, wearables, where you definitely need AI to provide this kind of seamless operations. Another field where it's important, or there's a lot of perspectives for artificial intelligence at the edge, is in terms of usability. And first is personalization of diagnostic, of treatments, of care. Is important. It's important to consider individual requirements, the different lifestyle, the environment, but also some potential cognitive or physiological impairments. And that's the potential that artificial intelligence at the edge has to consider this and to adapt to provide the best benefit for the people, for the patients, and also for the professionals. And last but not least, in this personalization issue, the aspect of interfaces and between human and machine is very important, and there's a lot of artificial intelligence needed in the device to provide better adapted interfaces here. In terms of safety and privacy, that's an increasing concern for users to have some devices that are safe and respect their privacy. So HAI provides or enabled an encryption direct on device, so that the data on the device and communicated from the device are safer, and to provide also truthworthy and explainable results. That's important for the people to understand what the device is doing, what the results are and why. And the last thing in safety and privacy is reducing the transfer of information is important. So if AI can contribute to this and avoid some unnecessary communication with the cloud, for instance, I think that's really important to reduce that. Here we see that HAI is important for patient empowerment, and that's kind of blurring lines between healthcare and pure health or medical applications, and also well-being. Yeah? People want devices that are somehow very easy to use. I took here the example of Diabeloop, a French company providing loop systems for diabetes management, where your smartphone is becoming a main actor in your healthcare. Another field that is really key for the increased use of artificial intelligence at the edge is, of course, decision making, and to provide a higher effectiveness in that. For instance, by filtering noise and directly from data gained in the device, reducing measurement error, increasing precision. And devices are acquiring a lot of data through multiplex sensing, and beyond that, we need to intercalate these data sets. That's an ability that artificial intelligence in the device should have in order to access to new knowledge. And the basis of that is to go from reactive to proactive. So to provide not only raw data, but to have both a contextual and a contextual information to better understand and to better take decisions on that. And of course, early diagnosis is key in curing diseases. So before symptoms appear, we need this a way to detect weak signals. Here, I would state that diagnostic imaging could really reach a new dimension with HAI. I took an example that's somehow important, also mentioned in the ECSS of portable ultrasound devices that are integrating some artificial intelligence. Well, we need also real read time. Why? Because it's we have to reduce latency to accelerate the processes, and reducing the distance of communication is important. But we need also to some extent an increased time resolution, because conditions are fast changing, and we need a very small reaction time here in order to enhance precision of health interventions. But at the same time, it's enabled to exploit swarm intelligence and to have multiple devices with HAI and to run parallel threads to solve complex problems and to optimize the resources. I would state here that closed loop systems and high precision tasks in medicine need this kind of HAI to gain in performances. And the last thing, we need a true continuum of healthcare, and HAI will contribute to that by filling the gap between the different phases, between well-being, pre-acute, acute, rehabilitation, and so on, and will increase the reliability of data between these phases. And another thing is we need to increase proficiency of stakeholders, not only of doctors and medical professionals, but also of a patient. That's with the help of AGI, I think it's possible. But we need interoperability of data between these phases. So that's why we need to align medical and digital standards, and that's an ability that AI has, as well as to support digestion of information from one stakeholder group to the other. That's why I believe that AGI has the ability to provide the necessary bridge here as an image that's in first response. The small company Archeon Medical in France is providing this kind of device to teach professional but also non-professional how to provide first responses and to save lives. So as a concluding remark, I would say AGI has the potential to contribute in tackling current challenge in healthcare, but it won't be the only solution. So that's always a combination, and working in the cloud, working in the device are two different aspects that have to be considered here. So, and that's it.
Great. Thank you very much. I think there's a couple of questions you can have a look over in the Q&A, and I say if not, I'll save them for the panel afterwards. So our next speaker is Matt Holdsworth from Lattice Semiconductor. So if Nicholas, you could stop your screen share, and then Matt, if you could turn your camera on and start yours.
Yeah. Let's see.
We can see you. That's good.
Yeah. Can you hear me?
Yep, I can see you and hear you. Can't quite see you. Oh, and your slides have just come up. That's perfect.
Excellent. Good. I see we are running slightly late, but okay. I think we'll get going, and we'll see where we land at the end of this. I'll try and stick to time. Yeah. So it's slightly different from me. I'm coming from a semiconductor manufacturer company, so clearly my background isn't directly in healthcare, but what we have is an interesting suite of applications specifically for AI at the edge. So, pretty good overlap with what you're talking about today. So just a couple of scene setting slides. So, regardless of whether it's healthcare or not, but within the world of AI, there's a really broad range of different ways that you can implement AI. And there are sort of some high level characteristics that sort of dictate what your target architecture would be. So, one is maybe what's your power budget? If you're doing handheld devices, then generally you'd be battery powered, and you don't want to be consuming anything that looks like watts of stuff. So, maybe you want to do extended battery life, or at the very least you want something to be running, for maybe an hour or two, quite realistically, if it's a medical device. Accuracy in healthcare generally is pretty high, but that's not always the case. You could have some relatively low accuracy, and you can also solve accuracy problems by accumulating images and running sort of AI processing on consecutive images to build up a confidence level. Similarly for latency. Now, latency, you would think you want it to be as quickly as possible, but that takes processing power. And so generally speaking, if you're capturing an image and running it, and you're happy to wait, for medical stuff, quite often you're happy to wait a few seconds, and that really the frame rate is very low there. You're just capturing an image and processing it offline. So, you can save a lot of power and a lot of processing power that way. And the final one down at the bottom there is to do with how much of the field of view is in, are you considering? So, and healthcare has a lot of different variables in play here. So if you're up close with, for example, the camera, and your face or your leg or whatever it is you want to take a picture of is dominating the picture, then actually you really don't need a very high resolution image, and you can get away with relatively low processing power on that, and the handheld device is quite realistic. If you're doing something more like scene monitoring, and you want to detect the mentioned earlier about falls in the elderly, or people moving around areas of buildings that you don't want them to, then this requires, obviously your objects are much smaller in the field of view. So you're, by definition, you're monitoring a much smaller area, and so you need a higher resolution to be able to have enough detail in that area. So all of these things tend to be considerations, and the higher towards the right is sort of higher amounts of processing power, which dictates a little bit the end form of the device. So to give you an example of some of the some of what we would consider to be true sort of edge applications, and some of these have healthcare implications directly, and some not quite so obvious, but would overlap pretty well anyway. So gesture detection is something that, although not obviously healthcare, but we are seeing increasingly that the desire to do hands-free operations. So in consumer goods, this is pretty straightforward because the consumer is pretty tolerant of things not quite working as needed. But actually, increasingly for things like automotive is quite similar to healthcare, that you really need a high level of precision. So the idea of being able to do gesture detection very accurately, but also on pretty low power. The good thing about gestures is generally you're pretty close up to the capturing device. So yeah, we've got some examples shown here. Gesture is actually a pretty good one for AI because your hand, with an IR sensor, your hand is generally pretty close to the thing that you want to do the gesture on. So we found actually we can do this in a very low power device. Battery powered gesture monitoring is really quite realistic. So presence detection, this would be something similar to detecting if maybe the elderly are moving around parts of the building you don't want them to, in a healthcare setting, or similar in hospitals, that sort of thing. So here, generally, you actually this version is more about detecting when someone is up in front of an object. So this might be if you've got a particular machine, a battery powered unit, you'd rather power it down when no one is around. This is a good example here, and you can do this in a very low power way because you've got, generally speaking, when the person comes up to use the equipment, they're in pretty close proximity to it. This one is probably more relevant though. This is very directly applicable to your elderly falling and looking for a particular body shape in a scene that's not moving. You'd want to do scene analysis, and you'd want to be able to monitor that. So we have, I should say, for all of these are all based on reference designs that we supply. So actually, a lot of the legwork is taken out of this. Just as a side point, we find generally, particularly in Europe, actually, the barrier to entry on AI is knowledge of the engineers working on it. Quite often there are a lot of good ideas, but actually getting over the line of actually implementing it and understanding how to do AI and how to produce an AI application is the biggest barrier. And so we've tried to make that as easy as possible with some of the reference designs that we supply. I got a couple of slides on that later, but they're all provided free of charge on our website. So interesting background if any of you are in the development side. And then similar object identification. So now it wouldn't necessarily need to be humans, but you could be looking for, and this is actually one of the areas where I mentioned previously was looking at data captured, and you wanting to detect certain features on a ultrasound or something like this. Actually, you've got, generally speaking, quite a lot of time to do that. So you and your device needn't necessarily have a lot of processing power, because you've usually got maybe a half a second or a second or something. Depends what the user would tolerate, but it might even be longer, several seconds. So being able to identify particular features in an image, and then it all comes down to the original training data set. So the examples shown here, obviously not applicable all to healthcare, but the example is the same. You capture enough examples of the thing that you want to look at, and then the object identification algorithm will provide a good, in some cases very good first pass at that, and give you a very high confidence level whether the thing is or is not in view. I don't want to talk through this because this is not the right audience, but just wanted to show this just to give you an idea from our side that when, if you wanted to start looking at developing a product, and we have some some companies that specialize in this area who are already quite well involved with us, we have a pretty complete suite of tools. So, that include the software side, the hardware side, the reference design side, IP, and so on. So, I would encourage you to make contact with someone from Lattice, you can just use sales@latticesemi.com or something like that. If you wanted to just get in contact, maybe you have a local contact. Depends what your organization looks like, but we have a pretty good set of tools that would help you get going as quickly as possible on that. Just a couple of things. This is not a sales pitch, but just a couple of things that are relevant here for things like healthcare. So one things, and we're down in the detail, but one of the things that we do is relevant for electronics devices is the idea of high energy particles that cause state changes in the device. So things as electronics get smaller and smaller, we find this becomes much more relevant because the amount of energy that's needed to change the state of a chip gets smaller and smaller. And some markets don't care about this at all. Consumer, to some degree, some industrial applications are quite tolerant of it, particularly any video type applications don't really care. But things like things like healthcare for certain, aerospace, anything with high reliability requirements where you really don't want a random error to occur, really start to pay quite a lot of attention to this. And this is an area where we've recently invested in a new process technology that has a very good immunity to this sort of error. So our devices are being adopted pretty heavily by the high reliability customers. It's related to the process node that we use. It's in the detail. I don't want to get into that too much here, but just to give you an idea that architecturally our devices are pretty well suited to, very well suited to high reliability applications such as medical. Similarly, I'll skip over this in detail, but we've done some architectural requirements which allow you to reduce the power. Generally speaking, you don't want to have as few external devices as possible. So we integrate as much into our devices, specifically designing them for AI. So you can expect when using particularly our low-end devices that for edge AI, they're a very good fit for that sort of application, which is also shown by the applications that we have. So just an example on if you get these slides later, you can see them. It's quite a salesy slide. It's not the right audience for it here, but just to show that we compared to something like an MCU, that's another pretty popular way of trying to do AI, or even something like an off-the-shelf dedicated AI processor. You can expect to get very good performance out of a low-end FPGA if it's been designed for AI. So just to finish, on our website, we have these reference designs that provide an excellent starting point for you. I would encourage anyone that's interested in just background detail on this for you to go and have a look at our website. There's a lot of good stuff anyway. You don't have to pay for it. You can go and have a look and download. There's with each reference design, there is a complete walkthrough guide. We provide the training material and the Python scripts and all of the all of the various layers of things you would need to be able to actually build a true AI application. And then tailoring it for the healthcare application or for your particular application is a case generally for AI. It's a case of training. Training data set, which is kind of unavoidable anyway for most AI applications. But we provide a very good starting point on that. And that's largely, I think, my final slide. Other than to say, I work for an FPGA company, so I'm going to be quite pro FPGAs, but they're a very good fit for AI applications. So I think if you work with a design partner or have a design department in your company, then they should consider it. FPGAs is a very good fit for edge AI in particular.
Great. Thanks very much, Matt.
So I will be talking today about Project Iris, which is designed to enhance the process of cell phenotyping from fluorescence microscopy images. So if you can move on to the next slide. So In preclinical drug research, the candidate compounds are tested on sort of artificial cell cultures. So at the top picture, you can see plates where these artificial cell cultures reside. So what scientists do is they treat those cells with the compounds, candidate compounds, and also they stain specific cell compartments with fluorescent dyes. And the microscope that you can see in the middle, it doesn't look like a school microscope, but it provides the capability of imaging hundreds of such plates in a single session, produces images. You can see an example image of the cell at the bottom left. And what the scientists are interested in is how potent are the compounds that they are testing, whether they do do cause the desirable effects on the cells. So the classical way of approaching the analytic process is quite tedious. It's lengthy. It requires a substantial expertise. And our job was to build a tool that will facilitate that process. So if we can move to the next slide. So we had built an application that it's a web-based application hosted on Microsoft Azure. So behind the scenes, we are utilizing deep neural networks that had been tuned for the cell assays. We allow for both supervised and unsupervised approach, which allows the scientists to both explore some specific hypotheses and also just explore the data to find out what's in there. So this is, as I mentioned, is implemented in Azure. So thanks to its scalability issues, the resources, the computational resources required scale accordingly with the growing number of users. And we have managed to reduce the processing times from several days to a few hours. And it gives us very similar results to what we had from the classical software. We can move on to the next slide. So this is the overview of how the pipeline works. So on the left, so we start with raw images. So each image contains hundreds of cells. We detect those cells using a deep neural network. We cut out the entire cells, and then we perform all of the processing behind the scenes in the back end. And this involves training a convolutional autoencoder to extract the features from the images and clustering the results just to allow the scientists to visually interrogate them. And this is an iterative process because the scientists can adjust the parameters and rerun the analysis until they're satisfied, and then they can produce the report. We can move on to the next one. So we have used the convolutional neural networks that are used in numerous computer vision tasks. So we use them to detect cells, to extract features, and to classify individual cells for the supervised approach. We use some dimensionality reduction combined with hierarchical clustering. So we also implemented active learning, which allows us to train models with relatively few examples. And everything is facilitated by the infrastructure provided by Microsoft Azure. So if we can move to the last slide. So just to summarize, these modern deep learning techniques can often serve as a replacement for classical computer vision pipelines. Despite their sort of intrinsic sophistication, we can make them approachable through easy to use graphical user interfaces. And because this was a bespoke solution, we were able to fine tune the product for the specific organization's needs. And Azure is a very nice platform that facilitates development of such scalable analytical solutions. So thank you very much. I think I managed to fit in 5 minutes.
That's great. Thanks very much. Sorry about that. My internet provider decided that it didn't like me anymore. So yes, up to our next presentation. If you could let my colleague know when you'd like your next slide, and please start when you're ready.
Yes, I'm Mustafa Al-Hamdi. I have a PhD in heart abnormality detection. I'm here to presenting Innovative Physics Limited, which is a new company that taking its foot into the artificial intelligence world and the medical side, and specifically on the radiation section. If you go next, please. Okay, so in innovative physics, we are very interested in a variety of sections of medical applications, starting from the lung cancer detection, and also not just for lung cancer detection and detecting tumors and segmenting them as well and giving an indication of the sizes of each tumor. Now, one of our interests as well belongs to the ability to detect CT scan images that are very clean. And that's why we're interested in the radiation part, where you use gamma sources to build those CT scan images. Now, prostate cancer and bone cancers as well, other interests that we are working on, and it's under development that may find its foot into the industry very soon. And clearly, as I'm the senior scientist within the organization, my PhDs belong to ECG and detecting heart problems. So we already have that system is really embedding into the company that we're trying to develop it even more to be a product prototype for the industry. So if we go next, please. So why we think that's really very important nowadays to include AI in the medical applications, mainly because of it's showing some promise. It's saving time for the doctors to do diagnosis instead of spending long hours looking at a couple of CT scans with the high resolutions. These AI models nowadays with the feature extraction methods can help a lot to pinpoint into region of interest for the doctors, not just time, but also accuracy. We, as human beings, we have the limitation of our eyesight. Well, machine learning can go deep down and extract features that may be not very easy to pinpoint by the eyes. And clearly by saving time, saving a lot of queues for patients to get into treatment or diagnosis, we are saving a lot of money. And clearly, we don't need a doctor to run all these tools. The doctor will be assigned some sort of supervision into the final outcome of the models, but it's going to be an operator. So ease of use is one of the factors. Please, next. So what we're trying to do really is take these information from the CT scans or the MRIs, and we're trying to extract where the regions that has abnormality compared to other sides of the brain or the lung or anything else. That's mainly what AI is trying. It's trying to do comparisons between benign regions and cancered regions and find the differences between those and make a model to learn those knowledge. So that's what we call it, the creativity. And we can see in the graph how the features of benign and cancered should be split in the space, and that will be the main task of the AI. Many tools can do that: dimensionality rejection, feature extraction, classification, clustering, whatever we call them. The main point is to split the features of benign and cancered samples on different space. Next, please. Next, please. That's just to show how the features can be extracted. Next, please. Next, please. So our lung cancer model, as the CT scan is really big, it's not easy to train a single model with the full size of CT scan. It's almost impossible. So we came with a method that we are splitting the lung into small boxes, and these boxes will include cancer or not. And then we train a neural network system to be able to give the probability of that boxes including cancer or not. That will include a lot of optimization and neural network training. Next, please. So this is one of the examples that we feel is very interesting. After we trained our model for neural network, the outcome will be X, Y, and Z, wherever the lung or the tumor that we think that has some cancer, and also the dimensions of it. So we'll be able to give a dimension for the doctor or anybody else to use this tool to tell your tumor located at that place with that dimensionality and also with a probability of that's going to be a cancer or not. We think those AI tools, as clever as they're getting with time, they will still need a doctor opinion to make sure they are really a tumor, or could be any other lung disease. Corona could achieve some sort of a tumors or similar shape to a lung cancer at some point within the lung. So we always give a probability, or what we think it's really a very interested nodules for the doctor to look at, and that's why we call it nodule probability. Next, please. And that's it for me. I managed to have another 40 seconds just to talk about innovative physics. I've managed to win a couple really of awards based on the work we're doing in the radiation and the medical side, that including the business and product innovation rewards for 2020, and also the South Coast Technical Company for our contribution in detecting neutrons in Fukushima in Japan, and also on the medical side. And thank you so much.
I think we might have lost Jane.
I'm here. I was just waiting for someone to introduce in the middle.
Great. Sorry about that. That was my internet yet again. So thanks very much. Please start whenever you're ready and I'll put my timer on. Thanks.
Thank you. So I'm going to quickly talk to you about some of the research activities that we've been doing for medical compliance for AI in the last year. Next slide, please. So this is me. My name is Jane Orme, and I'm a software engineer at Bluefruit Software, and we're based down in Cornwall. We are embedded software specialists, and we currently have 75 employees. So I'd like to emphasize that I'm not an expert. We've been doing AI for 1 year, working on an internal project called ACE, which we say stands for Audio Classifier Equipment. We take real-time audio and classify the sounds that it can detect. Next slide, please. At the start of our project, we identified some of the main challenges for AI regulation. The first that we thought about was the proving that the AI model was reaching the correct conclusions, which is quite hard if it's black box. So we wanted to not just rely on the test set, and this is because compliance, and in particular medical compliance, you don't want to have any mysteries happening within your software. And we also noted that the dynamic nature of the machine learning is another challenge. And this is because the model needs to regularly adapt to different changes. Next slide, please. Next slide, please. Thank you. So why do we want to know the internal workings of the AI model? And the goal here is to identify the problems early so that we can do a review, and we would do a code review similarly to how we might do. So we do a model review similarly to how we do a code review. For the opacity of black box algorithms, we can use deconfnets to see which filters the model has activated. And we can also use a GradCam to develop a heat map, which will show you the areas of the sample that the model is most focusing on. And I'll talk a bit more about that in a minute. For the dynamic nature of machine learning, we realized that there are parallels with Agile, and this is because it needs to cope with the regular changes. As a company, we've already got experience with applying TIR 45, which is the Agile for Medical Device Software standard. So we have applied some of this to our project. Next slide, please. What you're looking at here is an image of an audio file. In particular, this one is a 5-second sneeze, and the sneeze sound itself happens towards the start of the audio file. So we've converted the audio into an image. This is called a spectrogram. The x-axis of a spectrogram is the time, the y is the frequency, and the brightness is the volume at that frequency. So on the left-hand side of the screen, you can see our initial model. The original spectrogram is bottom left, and next to it is the heat map. And the heat map is showing that actually it's not focusing on the sneeze sound itself, it's focusing on the silence that happens after the sneeze, which is not really how you want to identify a sneeze. So we were able to remedy this. We added a silence category, did some retraining, and you can see from the images on the right that the heat map itself has actually moved slightly towards the start of the clip. So now it's actually overlaying with the sound of the sneeze itself. Next slide, please. TIR 45 mentions the different software development activities that need to take place, but actually it's quite flexible about the frequency and the order in which these activities might happen. So you'll have your design inputs, which might be your requirements or your design diagrams and that sort of thing. The output might be your binaries, your source code, or your test results. And TIR 45 says that if you're controlling these things, then you can finalize and approve them later towards the end of your project. which is a bit controversial if you're used to working in a more traditional way, where you would approve all your requirements and all your design and everything up front before you start your development. The image on the right actually comes from TIR45, and it shows your design inputs and your design outputs iterating as you learn new things. So what this means is it gives you the chance to experiment. You can try different design alternatives. You can adapt to feedback, perhaps from your user or your stakeholder. And also you might want to do further model training. You might find that your model, which works really well on your computer, gets good test set results, but when you try and run it on a device, you get slightly different results, so it gives you the time to do that. You can get different tools to help you. For example, Git can enable you to store and control the inputs and outputs alongside the code. Living documentation enables you to automatically generate the documentation. And test automation enables you to automate your requirements, which is called executable specifications, to generate test results. Being alongside the code means that they match the implementation and retain the traceability. And this enables you to iterate faster while being in control, improving quality and enable shorter release cycles. Next slide, please. And I think that's the last one. Feel free to contact me.
I'm now going to hand over to Victor, who should be waiting in the background. Victor, are you there?
Can you hear me?
I can hear you and I can see your slides. You're welcome to put your video on if you want. I'm going to turn mine off.
Okay. So good morning, everybody. Today, I'm going to talk to you about a very exciting development that we've made in the last 12 months. We've been working on improving a point-of-care diagnostic test to predict asthma attacks. And we've successfully implemented Edge AI on the device. And now we have the capability using deep neural networks to predict an asthma attack at least 3 days in advance. So this is the outline of my talk today. I'm going to talk to you a little bit about the asthma challenge across the world we face, tell you a little bit, explain to you a little bit about breath analysis, and then I'm going to show you a demonstration of what we've been doing with the development of our Edge AI breath test diagnostics. So applied nanodetectors' aim is to transform and change the way chronic diseases like asthma is managed to a more preventative approach, and giving people the tools to help them self-care and minimize symptoms and prevent them having asthma attacks. The way that we've been doing this is we've developed a point-of-care breath test, which can monitor markers of disease in the breath and predict the onset of asthma attacks. So how do we do this? This is a handheld device. And basically in that device, we have a chemical sensor array that's detecting these markers of disease. This handheld device can be used by any person, a child or an adult. And basically what they would do is they simply breathe into this device, and within 1 minute, they get the test results to tell them their diagnosis. And also using deep neural networks, we can predict the potential onset of an asthma attack. So as I've mentioned, in the device, we use a chemical sensor array that's detecting very low concentration, these trace biomarkers, which are down to the ppb level. This technology we're using has very high accuracy and high sensitivity compared to other technologies. Think of this like a mass spec on a chip, detecting many different chemical biomarkers simultaneously. At the same time, during the breath test, we collect physical lung function parameters. And what this enables us to do is to standardize our test. One of the challenges in breath testing is to make sure it's reproducible and repeatable. And by collecting this information, we can trigger the chemical collection of these biomarkers very accurately. And inside our device, we have embedded deep neural networks on the microcontroller that enable us to have predictive diagnosis. Unfortunately, asthma is a growing problem throughout the world. In the UK, it affects about 1 in 4 families. And you can see this is a very large global challenge. And this affects a phenomenal number of people across Europe. At least 21 million people are diagnosed. And there's phenomenal costs associated with hospital admissions and asthma attacks. In the UK, we spend around £1 billion a year on asthma attacks and asthma treatment and asthma medication. And unfortunately, about 75% of all hospital admissions are avoidable, and also 2/3 of the deaths are actually avoidable. So what are the challenges associated with the diagnosis and medical diagnosis associated with asthma? One of the key challenges that we want to diagnose disease earlier to give a more proactive preventive approach. And at the moment, there are not many objective tests that can be used to give the right diagnosis of asthma. We want to help people that suffer from asthma to have them symptom-free, but also prevent them from having asthma attacks. And what's important is to give people with asthma, severe asthma, these are people that may not be able to predict their asthma changes or a deterioration in their asthma, self-management tools, a medical device, a disease management software, where they can actually manage the condition daily in their home to prevent them having an asthma attack. So as I said, there are a number of challenges associated with the diagnosis of asthma. And one of them is looking at a more accurate test that could be used to diagnose asthma. In the UK, about 85% of people that present themselves with chronic cough is done in the GP primary care setting. So this could be a clinically based test that could be routinely used in the primary care setting. Asthma is a general umbrella term that's used for many different types of asthma. And really what's important is to identify the different subtypes. So then the patient can get the appropriate medication and more effective treatment. And where we're focusing today on this discussion is what can be done to predict and prevent asthma attacks. And so what we'll be developing is a point of care test that could be used daily in the home along the lines of a mobile application and disease management software, which can help them manage their condition more effectively. So on the basis of previous medical study, there was an extensive study looking at over 400 severe exacerbations, asthma attacks. And what this graph shows is you can see that at day 0, when the asthma attacks actually occur, there's a phenomenal change in the person's health. And what we can see here, if we go to the previous 5 to 10 days, there are changes in their respiratory conditions, their symptoms, and you can see there's a window here that you could potentially develop a test that could be used by daily monitoring to identify the onset of severe asthma attack up to 10 days. This window exists before there's a deterioration in the asthma. And so what we've been focusing on then is how we can develop our point of care breath tests to actually predict in advance the deterioration of people's asthma. So breath analysis has been known for thousands of years, okay? There are many markers that have been generated in the breath, which are markers of disease. And in fact, the NHS in the UK have already improved the provision of an NO biomarker, which can detect a specific subtype of asthma. Our approach at Applied Nanodetectors is to develop a test that can detect what's known as volatile organic compounds. Think of these like very volatile materials like ethanol, for example, which have been well known from many different clinical studies, which can act as non-invasive biomarkers, potentially identify different subtypes of asthma, and also potentially be used to detect different asthma attacks. And this type of sensing technology to detect these VOC biomarkers is something we've been working on in the last few years to bring forward a medical device. So what I'd like to show you here is 3 examples of how VOC detection has been used. And what's interesting here, if we look on the left, the very first early studies were shown that just by monitoring these chemical biomarkers in the breath, you can differentiate between people that have mild asthma and healthy controls. In the middle example, we can see here there's shown some research identifying the different subtypes of asthma. And on the right, further work was done to differentiate between asthma and other lung diseases. So there's a lot of evidence showing that the detection of these biomarkers can accurately help in a number of different diagnostic challenges for asthma. So I'd like to show you a short video now. And during any disease, there's a metabolic change. And what you see then are these metabolic biomarkers generated by the change in the cellular mechanism will be circulating through the body as generated by a change in inflammation in the body, okay, or infection. So these biomarkers, which are soluble in blood, will be circulating around the body. But what we're interested in is detecting these volatile organic compounds, which are volatile, non-invasive biomarkers, which are transferred to the bottom of the lungs at the alveoli. And then as you exhale, these volatile biomarkers will then come to the top of your lungs and be exhaled into our point of care test. Inside our point of care test, we have a sensor array that's been sensitized and specific to a number of different biomarkers, 8 biomarkers that can be used for diagnosis and also identifying asthma attacks. So as I said, in the last 18 months, we've developed a point of care AI breath test and a mobile application. And in this test, during the exhalation, we're collecting 13 different sets of data that characterize this exhalation in 4 seconds. This information, the combination of the biomarkers of inflammation as well as infection, we combine all these data sets together, and we've been working on developing machine learning capabilities to improve the diagnosis of asthma and also the implication of point of care test, a test that could be used close to the patient to help them predict an asthma attack. And what we use is a simple scoring system that 1, after a test means everything's fine. Score of 2 means there is a change in your asthma and there may be some intervention, which would have to follow through your action plan, which is included on the mobile application. And a score of 3 means potentially there's a serious change in your asthma and there needs to be a great change brought about by your action plan, but also to contact your care workers. Okay, so where does Edge AI come in for our benefit, for our patients? What is the real benefit of Edge AI? And the key challenge here is to give real-time feedback to somebody that's carried out a breath test. The breath test will be carried out every day on a daily process. So they would like to know straight away, once they finish this test, after a minute, is their asthma controlled or is their asthma not controlled? So we've developed algorithms that can be embedded onto our microcontroller. And the key thing here is giving a fast response, low latency to the user. Also, there's a significant challenge in making sure that we secure this information safely. And this can be done via encryption on the microcontroller itself. And secondly, this is a very low power solution. And so our device is battery powered. And so Edge AI can bring forward the benefits to use for people that potentially are trying to monitor their asthma in the home in terms of latency, privacy, and a low power application. Okay, so how do we do this? So as I said, we've embedded the algorithms on our microcontroller. We've done some external development of the deep neural networks, and then we developed a pre-trained model, which is based on the patient's condition, severity, whether they have mild asthma or moderate asthma. And then we're using a number of different software programs to then change these algorithms so they can be embedded actually onto the microcontroller. And we use a number of different software, including embed code, to actually can pre-train the model and put this on the device itself. So just to go through the steps in the process then. So now the algorithms are embedded on the microcontroller. The user then would use the device daily. And basically this would be via a mobile application. Okay, so the patient then would open up the mobile application through a secure login. And the first thing they need to do is fill out a simple questionnaire before they do any breath tests. Okay, and then they'll be guided through to take a simple breath test at a controlled flow. And then this information then during the breath test is then stored on the flash memory inside the device. Okay, all this information is stored on and analyzed using the deep neural networks. Okay, so then we use the deep DNNs to predict an asthma attack, let's say 3 days in advance. And we have an accuracy of up to 90%. And following use of this test daily, we can personalize this device and show more benefit to the user. So I'm just going to go through a simple demonstration. You breathe into the device. And here we see an example of the app, including the action plan and the help file. They would need to look at completing the questionnaire. I'm going to try to quickly show you a short video of the test itself. They would complete the questionnaire, and then they would breathe into the device for 4 seconds. And you can see this little ball moves up and down, and it helps the user guide through to make sure that they're exhaling at the correct flow rate. This information then is processed during using the deep neural networks, and then we can use this daily information to give them their score, which is a predictive model of an asthma attack. A score of 1 means their asthma's fine. And we can predict an asthma attack up to 3 days ahead. Okay. And so this is an integrated solution where the user would get the medical device plus the disease management software. And regularly daily use of this test, we believe, would be able to predict an asthma attack up to 3 days in advance. We've completed many preclinical studies. And what's exciting in 2021, we hope to clinically validate this technology through a number of different clinical partners and eventually start to test this in many different homes around the UK. So clearly here, using Edge AI is really developing a personalized point of care test that could be helping people with asthma to manage their asthma, but also prevent them becoming ill. So thanks for your attention.
That's great. Thanks very much. We're now going to go on to our second set of short presentations. And there you go, seamless interaction there from my colleague in the background. So if you could take yourself, Diana, off of mute.
Can you hear me?
Yep, you're coming through perfectly. And then remember to ask my colleague next slide, and I will press my go button on my clock, and your 4 minutes start now.
Thank you. Good morning, everyone. I'm Diana Hodgins, the Technical Director from Dynamic Metrics. And in my short talk today, I'm going to talk about our rehabilitation technology solution. Next slide, please. So what do? Well, we are a system company. We make a sensor system that measures how we walk. And the reason we do that is because everybody walks. It is something that we do automatically. We don't think about it. And we adapt our walk when we have a condition. So different medical conditions affect different joints. So knee OA is different to hip OA. And we can see that. These gait abnormalities can also increase the likeliness of falls, because falls generally occur because of an abnormal gait, osteoarthritis, or other medical conditions that can affect our quality of life. What we've then done is taken this data and we've developed what we call our virtual gym solution. which is an AI solution to look at exercises. Next slide, please. So what is this solution? Well, we've used the data and we drive a model, musculoskeletal model, so that we can identify which muscles are weak for that particular gait profile. So there will be some that are overactive, some that are underactive, some that are right. And then we also model all the exercises, and these are all standing exercises that people would use to help them in the walking function. So we've modeled all of those, and then what we do, we use machine learning techniques to marry up the best set of exercises that address the muscle deficiencies that we've identified from the gait. What the patient gets is their report, and I've given an example alongside here. The traffic light coding clearly identifies the patient and the healthcare official where the problems are and the severity. So if there's a lot of reds, there's a lot of issues. If they're all green, they're fine. And it helps people understand why they're going to get the set of exercises. There's a short list on the side that also shows I would like to, these are the exercises that will address the deficiencies. There's subsequent pages that give the picture of the exercises and also some words to say how to do them. So what does this do for the patient? Well, the patient for the first time actually understands where their deficiency is. And that's really important because up to now they get told, oh yes, you're moving better, or oh yes, we've worked on your hip nicely. They actually can see for themselves where the problem is. And of course, regular monitoring provides the motivation to improve. Next slide, please. So we are actually testing this. We're very fortunate that we're working with a hospital that is doing elective surgery, even in this COVID pandemic. And we're working with Norfolk and Norwich University Hospital and the University of East Anglia, measuring people that have just had hip and knee replacement. So we have an intervention group that we see at 6 weeks post-surgery. We test them and we give them their Gait Smart report with exercises. And then we see them 3 further times, each 3 weeks apart. We're also collecting the standard PROMs and the EQ5D, which is the standard metrics used by people. And we have a control group. So we can actually compare at the end of it, the difference in our intervention compared to the control group. The patient recruitment has started. We've got 9 people enrolled, which is a real achievement. And we're going to complete this in mid-2021. Next slide, please. So we do provide a cost-effective solution because conventionally it's a physio-led. This is actually technology-led. And if anyone's got any inquiries, please do contact me. Thank you.
Perfect timing. Thanks very much. Right then, our next person, Federated Learning for Analysis of Decentralized Wearable Sensor Data.
Can you hear me? Is that okay?
Yep. Perfect.
Okay.
Jamie. Thanks very much.
Perfect. So I'm a first-year PhD student at Newcastle University, and I'm going to be giving a talk on Federated Learning for the Analysis of Decentralized Wearable Sensor Data. Next slide, please. So the decentralization of data is a major challenge in healthcare AI applications. This is due to data not being centrally located. For example, we could have X-ray images that are located in different hospitals. And if we wanted to train, if each hospital wants to train a machine learning model, they may encounter issues because they're not exposed to the other training data. This is due to privacy constraints such as the EU's GDPR. That means that the simple amalgamation of all that data together to join train a model is infeasible. And the emergence of IoT devices means that a lot of personal data is being collected at a real-time rate. So we need a method of training AI models with decentralized data sources. Next slide, please. So this introduces federated learning, which is an emerging distributed machine learning paradigm. It allows for the joint training of a model over a loose federation of clients with data not actually leaving the edge device. Next slide, please. So I'm going to quickly talk over Federated Averaging, which is one of the more popular federated optimization algorithms. So during Federated Averaging, the central server has a pre-trained or an existing model, which exchange the model weights with a select group of clients. The select group of clients perform a few rounds of local training with their local data. And this model is then broadcast back to the central server, which the central server performs a weighted aggregation on the model weights, updates the model, and then selects a new set of clients for the next round of training. There's other algorithms currently in development, such as Federated Proximal and Federated Health. They're existing in literature. Next slide, please. So our work has been investigating the prediction of uneven and irregular surface conditions from human gait data. So we took this data set from the paper, A Database of Human Gait Performance on Irregular and Uneven Surfaces Collected by Wearable Sensors. It has 30 different clients and 5 different sensors in the study. We use data exclusively from a wearable sensor located in the left shank with an accelerometer, magnetometer, and gyroscope. And our challenge was to classify the different surface conditions with the data both being with the machine learning models being trained centrally and decentralized data sources. Next slide, please. So this is just a brief result from the work we've been doing. So in this result, we compare the model trained over a centralized data source and a simulated federated learning system with 30 clients in a network representing the 30 participants in the study. And what we found was that through using federated learning, we are able to produce a robust machine learning model that does not expose the client's data to the central server. Next slide, please. Yeah, and just to summarize, so federated learning offers a unique approach to training a machine learning model across a decentralized data source. It's a privacy preserving method which maintains the client's data to the edge device. And what we were able to show that is for machine learning applications in human activity recognition and gait analysis, that federated learning offers the ability to train a robust machine learning classifier. I think that's about it. Thank you.
Blimey, thanks very much. Nice. I'm going to turn the clock off now then. Great. So that brings us to our last of the short presentations, which is Richard Delegato on wearable AI. Are you there, Richard?
Hi, can you hear me?
Ricard, sorry. Yes, I can. I can hear you perfectly. So if you can let my colleague know when you'd like the next slide, and I will pop the clock on.
Great, fantastic. Thank you for being here. I'm very happy. My name is Ricard Delegato. I'm from CSCM, that some of you may know. I'm the head of the embedded software group, and today I'm going to talk to you about wearable AI. So I'm going to try to push a bit this concept of edge. Next, please. So for those who don't know, CSCM is actually a public-private partnership. So we are an RTO like Fraunhofer and companies like this. So we develop the technology and then we transfer it to the industry. So I just want to get this out of the way, so you won't find a CSCM product on the shelves. Usually we transfer technology, we create startups, we make the IP and so on. We are for non-profit, so anything that we do, we reinvest in let's say in new research. Can you just go for the next one? Yes. So in terms of wearable, we've been on the market for we've been an active player for a long time, usually in different form factors. So right now it's quite trendy, the fact of having like a wristbands or a smart watches, but we have been as well like playing into shoes, or what we call right now is the smart headphones or hearables as well. The same thing for patches, either adhesive or something embedded in clothing. And as you can imagine, all these devices are pushing the definition to the edge to really something that you have to wear, and you have to be like really low power, right? Can you just go to the next one, please? So we can all agree that machine learning is really disrupting the classical machine learning algorithm, the classical algorithms that are embedded into small devices. So we used to develop quite a lot of and optimize signal processing based algorithms. So in fixed point implementations and SIMD instructions, so on and so forth. So machine learning and in particular neural networks, which are quite trendy right now, are also suited for this kind of optimization. And we agree that there actually are like three main drivers that are pushing us to start using these kind of algorithms inside the device itself, instead of in a backend or in the phone or in some kind of gateway. Right. One of them is data privacy, right? If you're monitoring some kind of vital sign, if it doesn't leave the device, then somebody cannot infer more information than necessary. There is a very important thing of latency. There was a discussion today about what is actually real time. For us, if you have to send something to a cloud and come back, you can make it very fast, but the latency becomes an issue, right? So I struggle to call this something like that in real time. So for us, the algorithm, the machine learning algorithm should be deployed into the device itself. And clearly the power consumption. So machine learning based algorithms are much heavier than traditional signal processing. However, sending raw physiological data through the Bluetooth or Wi-Fi and so on, it's also very heavy. Just go to the next one. So just to show you, we like to show you a small use case that we did in-house during this past year. We focus on one of our prototypes that you can see here on the right is a 2-lead ECG. So it registers, you have like a Swiss franc next to it, so you can imagine that the size of the devices. It has like an onboard memory, Bluetooth, and so on and so forth. And we deployed one of our neural networks, the one you can see below, for detecting cardiac arrhythmias. So in how we proceed is like we took this model that it was trained on a large database on a cloud, and then the model was compressed, quantized, and implemented into a system on chip. In particular, we used the Nordic Semiconductor's NRF52, which it has a floating point unit, but our implementation that doesn't actually need that. So in terms of trade-off, as you can imagine, there is always, the more compressed your networks, the worse result you may get. But if you go to the next one, please. Okay, here is, I would say, maybe click once more so it appears. Okay, so here is the landscape of the different models which are competing to ours in terms of accuracy. Just check on the horizontal axis is in logarithmic, so you can see how quickly the number of parameters just skyrocket. However, as by the way that we have for compressing the networks, we can lose a bit of performance in terms of F1 score, but actually we can easily get one order of magnitude below in terms of matter, which makes it embeddable. Just to finish, on the right, you can see TensorFlow Lite is starting to implement similar tools to ours. We can decrease quite a lot in terms of energy and memory footprint. Next one. So this is my conclusion. Thank you very much. If you have any questions in terms of embedding machine learning, I'm happy to answer.
Great, thanks very much. So if anyone has any questions for the short pitch presenters, please use either the meeting mojo, I've just reposted the link into the chat, or use the chat. I have a question for you, Ricard. You put a question into the Q&A, and I wasn't sure who it was aimed at. So your question was, have you considered malicious data sources, as I've still got you on the line? Who was that a question to?
So it was just the presenter before me. I don't remember his name. He was talking about federated learning.
Yes, from Newcastle. And my brain has gone completely dead on me as well.
Jamie,
so
Jamie McQuire, exactly.
Yes. Jamie, you still around? Yeah. So the question to you, as you see here, is, have you considered malicious data sources? Was a question Ricard had for you. Just thought I'd quickly ask that because we've got a couple of minutes.
Is that it?
Yep.
Yeah, so we haven't considered malicious data sources yet, but I know there's a bit of work in federated learning with people who've explored data poisoning attacks. So this seems like there has to be a sort of incentive mechanism involved when training an actual system.
Great. Okay. Thanks very much. I have posted, there's a number of questions have come in on the Q&A for the short presenters. I've posted them all into the chat. It looks like most of them have been answered, but if our presenters would like to have a look into the chat box, which you can get by clicking at the symbol on the bottom of your Zoom bar, it'll appear on your right-hand side, just to see if there's anything pointed at you. I say I've put the meeting mojo in there and people can connect to each other. If anyone doesn't manage to connect to someone, they can contact me or the KTN via the events team that have contacted you and ask to be connected, and then we'll try and help you in the background post-event. I'm now going to come on to a short panel session for Q&A. I must say, you've been like lightning in the background answering nearly all of the questions which have appeared. So if anyone has any questions, we do have some time. I've got a couple of questions that have come in that I'm going to ask live now. Both are for Victor, so you've lucked in there, Victor. The first one is a quick one, possibly, which is, is this considered a medical device, your asthma?
Yes, it's actually classified as an IVD, intravenous IVD diagnostic. Great.
So hopefully that's answers Stelios's question. And then the next question, again for you, Victor, has come from someone I've known for a while, Sergio. And he said, well, actually, this is an open question to other speakers as well. What is the AI part of your development? So to elaborate, many methods in this field are data-driven, where outputs depend on parameters that have been learned or derived from training. Are people equating AI with deep neural networks? So that's actually a question to everyone, but I'll start with Victor.
I think the reason we've implemented deep neural networks is that what we're trying to understand is what we need to measure, or what's different between different subtypes of asthma that can be indicative of an asthma attack. So even though the person would use the device, it would be personalized, and you use the DNN to learn what are the changes in or deterioration in their asthma. All this information would be eventually collected through a hybrid model of looking at many different patients. So it would personalize for the user, but then you'll be collecting data using this device from other patients. So you're using a combination of deep learning personalized unit plus machine learning on many patients' data to combine that to more accurately predict an asthma attack.
Okay, so I suppose the question goes to Matt and Elizabeth as well. Is it deep neural networks? Is it machine learning? Is it AI? How do you see the difference in these and what you're applying? Matt? I think we may have lost Matt. Yes, I think we've lost him.
Yeah, he's not online.
Right. I'm glad I'm not the only one whose internet provider hates them today. So I suppose I think we've answered Sergio's question there. I think I've got gonna have a quick look to see if anything else has come in over here on the chat. Okay, so that's a question for. Okay, so there's a question coming for Victor again, but I've got a question for, I think actually this could be for Elizabeth, Victor, and Nicholas. Really, it's around what do you see or what have you discovered as the principal regulatory challenges in achieving adoptions of new technologies? So especially where you're putting AI machine learning into embedding it into devices, what are the key regulatory challenges that people are facing? So Nicholas and Elizabeth, if I ask you from a general principle of what are you finding within the community you're talking to?
Yes, Simon. Yeah, basically we are at the convergence of medical regulation, but also of privacy regulation, and that's what is making the world topic around regulation quite difficult, because you have to comply with quite tough medical regulation, from the medical device regulation, for instance, which has been reviewed for some time ago, which is highly regulated and on national basis. With, for instance, GDPR regulation. So there's some challenges indeed here in how to comply with both sides of regulations. Yeah, but
okay. Elizabeth, do you have any thoughts on this? You're on mute, by the way.
Yes, sorry.
That's okay.
I have nothing to add because I'm not the expert in this kind of regulations. For my
No, that's fine. I just didn't know if you had any anecdotal conversations.
No.
No worries then. So, Victor, how are you finding this? Are you coming up against any big regulatory challenges? Any ones that stick out particularly to you?
No, I think, as you said, there's obviously data, personal privacy of data, how that's being used. But I think what you've got to be really clear is the value proposition. So if you can give somebody a device and you can demonstrate to them it can really improve their health, I think, although you have to build into the system, which we already have, during the login, it's all protected for general data protection, and everything we do is made sure it's protected to meet regulatory requirements. I think the adoption challenge is not so much around the regulatory, it's going to be around the real value of using something based around AI that can predict and prevent you becoming ill. And I think the value proposition maybe is something we have to, as a company, focus on. Many people we've had from focus groups are really positive about having the technology, and I don't think they're so concerned about the personal data accessibility, although that is an issue. They're more concerned about having something that's really going to change and improve their quality of life.
Okay, oh, good. Question for you, Victor, on your particular application came in. Does the user had to have had an attack in order for the learning, or can it take learning from other users, if that makes sense?
What we do is that each person, ideally, even if they've had an attack, if you think about how the device actually is going to work, is that the first day you use it, it has very limited information in terms of potential ranges, sensor outputs that you can put in the system and say that you'd know that potentially if you have an asthma attack, these sensor outputs would be definitely changed. For example, your Excel flow rate would be very low. So you can start to do that. And I think what we've learned so far, it takes about 3 to 5 days to train it using your personal data. So even though if you've had an asthma attack, it doesn't limit that. What it's trying to do is customize it for you as an individual. And that's where I think the value of the deep neural networks is trying to learn what are your normal levels and what are your levels that could be leading to an asthma attack.
Great, thank you. So got a couple of questions in the Q&A over here that haven't been answered yet. So there's one that's come in from Mary asking about haptics, but I believe that was Matt Holdsworth who was the main person talking about haptics and touch sensing. But I'm going to ask the question and see if anyone has any thoughts on it. So haptics as a route to user engagement was mentioned earlier. Would any of the speakers care to comment on how they, if they work with the textile industry on those sorts of aspects in their product? Also looking at challenges faced to overcoming the integration of electronics. So I don't think anyone on the line is dealing with materials specifically in their electronics, but I'll give people a sec to take themselves off mute if they are.
Yeah, Simon, I could take that. Nicholas here.
Okay,
that's
yeah,
true. We are not directly dealing with textiles. That's true. But and that's exactly the reason why we have some tight and close relation to the textile industry through a similar structure as EPoSS, so the European Technology Platform. We are working with Subsea, that's a sport innovation platform, which deals with more the applicative side of sports. So, and textile is one of it. And for instance, we organize our last annual forum together with the sport people, so that we can have this interface between smart system integration and textiles, for instance. Yeah, so we are not the textile guys, but we do have, through collaboration, have access to this particular field.
Great. Okay. So if Marie's still listening on this call, I've just looked up who I think you are on LinkedIn. I will drop you a line with a couple of UK companies that that we're aware of in the KTN. Infotex is one that's doing textiles that are touch sensitive that have a medical application. And there's also a sports company using textile wearables for sensing. So I can send you some details on those companies and what they're doing as a follow-up later after the event. So an interesting question, I think, for Victor and in specifically, but also I think Nicholas and Elizabeth may have some thoughts. Polluted databases, so data lakes for AI training. Have you come across any issues or had to take into considerations how to avoid having those problems and giving you false information when you've been looking at when people have been looking at setting up systems in the first place?
Hi, I think specifically for our device, we'll be utilizing data that's actually come from people using the technology, because we're collecting unique biomarkers and we're collecting other lung function measurements. So I'd say we wouldn't face that because we're tending to learn more from the use of the device rather than using external data sources. The only rare area we might use external data sources is pollution, air pollution. So we'd like to obviously see how air pollution changes or affects as another trigger for asthma attacks.
Great. Okay. I mean, so Nicholas and Elizabeth, has data purity or data security or trustability come up as anything that's been discussed in conversations that have been happening in the people that you've been bumping into?
Well, basically, I'm not a data scientist, so I can't. What I can say is smart systems and electronics is important to generate the data, to transmit the data, and so on. So trustworthy electronics is definitely a field of defined as a strategy for the future. That's for sure. And what I wanted to say, yeah, that's why we see also a field of application for AI at the edge as explainable AI, yeah? so that we can reconstruct how the AI is working and based on facts. Yeah, so that's basically how we see from the data generation side how we could avoid at least pollution.
Great, thanks very much. I think I'm actually gonna say we're gonna let people go a few minutes early and just really draw things to a close now. I first of all wanted to say thank you very much to our speakers. I also wanted to say thank you very much to our sort of short pitch presenters. We've not done it at the previous events, worked really well. And I think it gave an interesting, different set of dynamics and some really rapid drops of information that's been really getting some great talk going on in the chat. And so hopefully people can continue that on the Meeting Mojo as well once the event has come to a close. We are going to start planning future events for the new year. There'll be a feedback form coming out. That is the perfect opportunity for you to tell us as the community what topics and areas you're interested in seeing discussed. So yeah, you know, we've talked about healthcare, we've talked about mobility. There's been a few other topics covered in the series, but what is it you want to see for future events on this sort of theme of where embedded AI is making a real difference? So this event has been recorded. A copy will be sent out to delegates who registered shortly. Give us a few days though, along with probably copies of presenters' slides if they're able to share them with us. And my colleagues put the Meeting Mojo link back in the chat again. But yeah, thank you very much for joining us. I hope people have found it an interesting event. And I wish everyone has a good weekend. Thanks very much for coming.